Dear students, welcome to another day's lecture in Elements of Machine Design. We were discussing the design of springs. So we have seen um, one problem solved yesterday. So today we will solve some more problems. See this problem. A closed coil helical spring is used for an automobile suspension system. The spring has, say, automobile suspension system doesn't mean that it should be leaf spring. It is sometimes given helical springs are being used. And closed coil means, the helix angle is less than 10 degrees. That's all, nothing else to do. It is a closed coil helical spring. That is what we have to design. You remember that. The spring has a stiffness of 85 Newton per millimeter with the square and ground ends. See, the four end conditions are there, and this is that square and ground ends where inactive turns will be 2. Otherwise, the total number of coils will be effective coils plus 2. That is n dash is equal to n plus 2. That formula we have to use. The load on the spring causes a deflection of 9 millimeters. This is the delta. Is it delta maximum? No, because load had been increased, it would have been more. So it is not delta maximum, it is delta. Okay. By taking permissible shear stress of 400 MPa, this is tau 400 MPa, find wire diameter of the spring, then the length of the spring. Length of the spring means, you see, it is a free length. You see, I told you even yesterday, if it is simply said length of the spring, it is free length. If it is the length of the wire, then it will be the wire. If the spring is stretched into a straight line, then that length will be will be showing. Okay, take spring index is 6. Spring index is 6 means C is equal to 6. So C is equal to 6 means, Wahl's correction factor, that is, um, if you are using, that will come to how much is, that will be 1.2525 will come. Okay, G also is given 80 into 10 to the power 3 Newton millimeter square. So what are the things that are given? Stiffness is given, spring index is given, squared and ground ends, so inactive number of coils is 2, deflection is given, delta 9 mm, G is given. So we know spring stiffness is load upon deflection. See, load upon deflection, that is F upon delta. So from this, because you have K, you have delta, you can find out F. See, this is one way of giving the problem. Instead of directly giving F, they are giving these two values, and you have to find out this. So F is equal to K into delta, that is 85 into 9, 765 Newton per newtons. Okay, now Wahl's correction factor, 4c minus 1 upon 4c minus 4 plus 0.615c. So in that, now kW will be 1.2525 if you substitute the value of c. Okay, and now we have one formula, the shear stress formula, tau is equal to kW into 8 fc upon pi d square. See, in terms of c, this is, had it been d upon capital D upon pi d cube, it would have been. But because we are using c, okay, this is c upon pi d square, it comes. Okay, see, it is not much confusion. It is the same formula which can be written in terms of c also. Okay, now substituting all these values, you will be able to find out what is d. D is coming to 5.7. You can round it to 6 mm. Now what you have to do, now you have another formula, delta here also. In terms of c, we have taken, had we used capital D, it would have been capital D cube upon small d to the power 4. It would have become the same formula. It is written in terms of c. If you are writing in terms of capital D, it will be something different, and in terms of capital C, it will be like this. Okay, So the number of turns, number of coils, you say, can be written like this, rewritten like this. From this, if you put all the values, you will get 3.1, or that means 4. So now what is the length of the spring? Length of the spring is, free length of the spring is n dash d plus delta maximum plus 0.15 of delta. Okay. So, okay. It is actually, this is not a delta maximum 9, but here they are having no other information. So we are assuming that it is subjected to only 80 Newton per Newton's force. Is it 80 Newtons? No, 765. Oh yeah, F is 765 here. Only 765 Newtons is coming. So this itself we have taken as delta maximum. Okay. So n dash will be what? N plus 2, that is this 4 plus reactive plus 2, it will be 6. So this is 6 into 6 plus delta maximum, 9 I have taken, and 0.15 into 9. So this is the length of the spring. So then in that case, you don't write as free length. You simply write length of the spring, because above that it is not allowed to expand. Okay, then this is the length of the spring, is it? Length of that spring, given spring. So the free length will be when delta maximum is there. Then in that case, this formula should be length of the spring n dash d plus delta you use instead of delta maximum, and 0.15 delta. See, like that you can solve it. So length of the spring will come to 46.35 millimeters. So as this is length and we have nothing to do, no need of rounding this. Okay, let us see another problem. Now this problem. A helical spring is made of a wire of 8 mm diameter. What is this 8? Small d, 8 mm. And the outside diameter 90 mm. Outside diameter means DO. It is not mean diameter. You see, the diameter for the coils can be capital DI, capital DM, or capital DO. Now this is the outside diameter means DO. Can you find out DM from this? Yeah, uh, DM will be outside diameter minus the wire radius. That means 90 minus 8. That means 90 minus 8 will be 82. 82 will be the mean diameter. You see, they have not directly given us mean diameter, so a little twisting is there. You should be able to understand this. Okay, if the permissible shear stress, say tau is given. Tau is 350 Newton per mm square. Modulus of rigidity 84 kilonewtons per mm square. This K should be small letter. Here they have written capital. Say kilo is always small k. Okay, then find actual load. Now load they are asking. When the spring can carry, which the spring can carry, and deflection per active ton. You see delta also they are asking, and load also they are asking. Neglecting the effect of curvature. Oh, till now we are considering the effect of curvature. Neglecting the curvature, the effect of curvature means that value of k will change. Then second condition is considering the effect of curvature. Okay, we will see both how to do it. Now what are given? Diameter is given, also diameter is given of the coil, shear stress is given, modulus of rigidity is given. Then mean diameter can be calculated as mean diameter, outside diameter minus wire diameter is 82. Now we have the spring index. Now spring index, yeah, spring index C is mean diameter upon D, D upon D. So this is 82.8 is 10.25. This is case 1 where you are neglecting the curvature effect. Curvature effect means Wahl's correction factors will not come into picture, and the previous Now we have the twisting moment. Twisting moment can be given as torque is equal to F into radius dm by 2. You see, this is nothing but, you know, T is equal to pi by 16 d cube, tau d cube. So from this, considering these two, F can be written as pi by 16, and this comes here, so 2 by dm tau d cube. So this 2 cuts and 8 remains. This dm is 82 and tau is 350. From this now you can find out what is the actual force. Okay, this is purely without considering the Wahl's correction factor. We have the delta formula. Delta formula is this: 8f cq upon gd into n. Otherwise, it will be 8f d cube upon gd to the power 4n. Okay, but in terms of c, it is this formula. Now, deflection per active turns. This is active turns. This is deflection. So, bring it here. So, this will become deflection per active turn. That's what they asked. So, here you substitute, it is per active turn. It is coming to 11.002 mm. This is without considering the curvature effect. That means without considering the Wahl's correction factor. Now let us consider the Wahl's correction factor. Now when we are considering the Wahl's correction factor, say Kw C is equal to 10.25. This 10.25 we have calculated before. So Kw comes to 1.141. So shear stress induced in case of we considering the Wahl's correction factor will be this in terms of C. Okay, then you substitute all these values and you will get uh, F is equal to this much, 752 Newton. Is actually, when we are not considering the curvature effect, this was coming to around 850 or something. That means what? Because of the curvature effect, you see, lesser load itself will cause that much damage. That is the meaning. Then the deflection per active turn delta upon n is required. So you substitute all this. Now, because the load is reduced, the deflection per turn also will reduce. This comes to 9.641 millimeters. Okay, now let us see another problem. Design a helical compression spring for maximum load of 800 newtons. This is the maximum load and a deflection of 25. See, this deflection is for maximum deflection. This is delta maximum. This is real delta maximum because this is the real maximum load. Okay, that means beyond 25 it won't go. Okay, the spring index is 5. This is C, 5. Wahl's correction factor is directly given as 1.3. The maximum permissible shear stress tau is given as 400 MPa, and the modulus of rigidity G is given as 84 kilonewton per mm square. All these things are given. Okay, now what are they saying? Only design here saying. Design means what? Okay, we will find small d, capital D, and what else we can find? We can find the free length. Such things we will find. Okay, now come. See, we have the one formula. Tau is Kw into 8fc upon pi d square. So from this you can get diameter. That is coming to 5.75. It is, you can round it to 6. Another formula you have delta formula. From this now, number of turns you can find out. Number of turns is coming, number of coils, sorry, active coils. Okay, you can check number of turns, active turns also, no problem. So n you're getting 14.96, so 15. So if it is like that, then as now they didn't say the end condition. Okay, now we are saying and it is we are assuming square and ground ends, so it is n dash is n plus 2. If this is coming 15, totally it will be 72. Sorry, it is 17. N dash is 17. Now the free length of the spring is n dash d plus delta maximum plus 1.15 of delta maximum. So n dash you got 17, d is a 6 we got, delta maximum 25 already given in the question, and then we substitute. So when we are substituting, it comes to 130.75. That is the free length. Pitch also you can find out. Pitch is a free length upon n dash minus 1. These are the number of gaps. Free length of the spring is that 130.75 upon the gaps is 1 less than the number of coils, total number of coils, that is 16. So it comes to 8.17. And you can find out the mean coil diameter. Mean coil diameter, we know we have this formula C is equal to dm by d. From this you can find out dm 28.5. We can find out the outside diameter. Outside diameter is mean diameter plus d. Inside diameter is mean diameter minus c. So these two values also you can find out. Okay, let us see another problem. Design of helical spring for spring loaded safety valve. See, whenever safety valve is coming now, they will give pressure and you have to find out the force. See, then they will, okay, little twist will be there. Okay, operating pressure P1 is 1 Newton per mm square. Maximum pressure when the valve is blown off freely is P2 is equal to 1.075 Newton per mm square. See, for maximum, considering the maximum load, you have to use maximum pressure. Okay, then maximum lift of the valve when pressure is this delta. This can be taken as delta maximum 6 mm. Okay, diameter wall seat is given 100 mm. So this is for calculating the load. Okay, wall seat, it's not the diameter of the coil. You understand this? This is nothing to do with the spring. Okay, maximum shear stress in the spring is 400 Newton per mm square. Modulus of rigidity of the spring material is 86 kilonewton per mm square. Spring index is 5.5. These are all given. Sketch the dimension of spring also. Oh, they're asking you to sketch it. Okay, you should be able to draw a rough diagram. Sketch itself means it's a rough diagram. It's not to the scale. Okay. So now the wall seat is given. So the wall area we can calculate from this. This comes to pi by 4 dV square. So it comes to 7,853 mm square. Now the force, uh, the initial force before lifting of the wall is, you see, pressure is load upon area. No, pressure is load upon area means force, load is area into pressure. Area into pressure, you will get this value. And maximum force, if you want to find out, you have to use pressure, not 1, you have to use pressure 1.075. This is the maximum load and this is the okay, you can say that initial load. This is the maximum force, 8443. Okay. Mm. One thing you should understand is, see, here operating pressure, see, this spring is already compressed. You see, it's already in compressed state, it is not free state. So for this operating pressure, uh, which is already compressed, and for maximum pressure, it will compress further. So how much, and here, you know, this delta that they are saying, maximum lift of the wall when the pressure is this means 6 mm. This 6 mm is from this pressure to this pressure only. That means what? Here one load, one force you are getting, here another force you are getting. So अभी ये फोर्स से ये फोर्स तक का जो डिफरेंस है उसके लिए ये डिफ्लेक्शन होता है. Okay. See, now we have calculated two forces here. One force is this maximum force 8443. Another force is 7854. You see, for 7,854 for 7,854 newtons, it was already compressed, and when more force comes, no, it is compressed by 6. So, what the total force which causes the deflection is 6 mm. So, what total force is what? The force, no need of total here. The force which causes the deflection is F is equal to F2 minus F1, F 589 newtons. This 589 newtons is responsible for the 6 mm deflection. Okay, this is what we have found out. This is only the difference, in the other problems and this problem, how to arrive at this thing, 589 newtons. Okay, then Wahl's correction factor, you get 1.278. Then we have this formula, tau formula, in terms of D, in terms of C. Okay, so but we know C, so we can directly use this formula. From this you get diameter 19.439, and uh, you can round it to, you could have rounded to 20 here. Okay, anyway, he has not rounded, I don't know why. You should have rounded here. Then the mean diameter will be, from the spring index, we have spring index C is equal to dm by d, otherwise dm is equal to C into d. So 5.5 into d, this comes to 106.9 or 107. Okay, outside diameter, inside diameter, all this, and number of active turns. For number of active turns, the other formula you will use, delta formula. So from the delta formula, if you substitute, you will get number of turns as 12.49 rounded to 13. And here he is assuming ground ends. You can assume anything, when you are assuming. If you are assuming square and ground ends, then you have to put n dash is equal to n plus 3, but he is assuming ground ends, so n dash is equal to n they is taking. So now the free length will be solid length plus maximum deflection. This formula, n dash d into delta maximum into 0.15 delta also you can use, or this formula you can use. Any of the two you can use, no problem. So from this you will get the free length, free length of the spring. And delta maximum you can calculate like this. If for 589 newtons 6 mm is resulting, for 8443 how much it will result? So that you will get delta maximum is equal to delta upon F into F maximum. Okay, so from this you can find out this will be 86 mm that could have been, so that will be the maximum deflection from the free length spring to the maximum that you can press is 86 mm, and this is the force that causes the maximum deflection. Okay, so pitch of the coil is free length upon n dash minus 1, this one, free length you have got 339.79, and this is 13 minus 1, so you will get pitch of the coil. Now they said you draw the diagram. So for drawing the diagram, you can show the cut section like this. See, like this. This is the diameter 19.43. This is the pitch. But if you are rounding it to be 20, you will be showing 20. Then accordingly, this pitch also may vary. Okay, doesn't matter. See, in design, everybody's answers will not be same. Then DI, DM, DO, this much you can show. The sketch means what else can you show? This much you can show. Okay. So with this, this problem we have solved. Let us see some other problem. This also is asked 3 times in the exam. A closed coil helical compression spring of 12 active tons has a spring index, a spring stiffness of K. So it is not, K value is not given, so it is given as K, so whatever we are getting will be in terms of K only. Okay, it is cut into two springs having 5 tons and 7 tons. You see, 12 coils spring is cut into two springs, So one is 5, another is 7. Determine the spring stiffness of resulting spring. If spring stiffness of the initial thing is K, what will be the spring stiffness of the resulting things? Okay, let us see. So number of active coils before cutting is N is 12. After cutting is one spring has 5, another spring has 7. Now, um, now spring stiffness. Spring stiffness formula. Spring stiffness means what? F upon delta. F upon delta is not there in the shear stress equation. We are having two equations, but in the delta equation you will have stiffness value, stiffness formula. So stiffness is F upon delta. So these two values you take out. What will be remaining is Gd to the power of Gd to the power 4 upon 8 d cube n. This will be the stiffness. So because they are asking about spring stiffness, we should find out spring stiffness. Spring stiffness K is F upon delta. So in this formula, these two can be found out. That's why we are using deflection equation, not the shear stress equation. Okay. So here now, for a given material, G is constant, and before cutting, after cutting, the diameter of the wire is not changing. Before cutting and after cutting, mean diameter is not changing. What is changing? Only N will change for different springs, different number of coils. Okay, all the other things are same. Otherwise, what we can say is, we can say that Gd to the power 4 upon 8 dm, this is all one constant, you can say, x. So simply you can say, now spring stiffness K is equal to F upon delta is nothing but x. This are all x means x upon n it will become. Okay. So for from here, from this two, see what is x? X is K into N. K we have for uncut spring is 12. So 12K. No, sorry. For N is 12. N it becomes 12K. So for let K1 be the stiffness of the cut spring with 5 tons. K2 will be the stiffness of the cut spring with 7 tons. Okay. So we have N1 is 5, N2 is 7. So what will be the stiffness? Say what will be the stiffness? It will be uh, the same thing here what we are using. K1 is x upon N1. So this is x we know to be 12K upon 5. This is 2.4K. If it is K2, it comes to 1.7K. That's all. This is the answer. That's how you have to say. And sometimes no, suppose what would have happened if this is 12 active turns and this is cut exactly half, that means 6 6. If it is cut, what will happen? See, if this is 6, how much it will become? It will become 2K. If this is 6, it will become 2K. Are you understanding? If a spring is there, if you are cutting into exactly half, then the spring stiffness becomes double. Okay, this sometimes can be asked in the quiz. Okay, okay, let us solve one more problem. A rail wagon of mass 20 tons is moving with a velocity of 9 kilometers per hour. You see, some velocity also they are giving. That means, then you may have to consider kinetic energy and all. Okay, we'll see. It is brought to rest by using two buffer springs. See, two springs are there. Two buffer springs of 360 mm diameter. So this 360 mm diameter means this must be the dm, capital Dm, that is the mean diameter of the coil. The maximum deflection of the springs is 300 millimeters. This 300 is delta maximum. Okay, the allowable shear stress for spring material is 800 MPa. This is top. Design the spring for buffers. So we have to design. You see, now Uh, now what is given is M is 20 tons. 20 tons means what? 1 ton is 1000 kg. So 20,000 kg. Velocity is 9 kmph. That is, if you want to convert it into seconds, it becomes kilometers. Kilo is 1000. Hour in 1 hour 3600 seconds are there. Hmm? So you will get 2.5 meters per second. Then dm is given, delta is given, tau is given. Okay. Now for the wire diameter. Now kinetic energy. Kinetic energy is, we know kinetic energy K is half of mv square. So m we are having, v we are having. So put this. So kinetic energy is so much. Okay. Then now let F be the equivalent load which is applied gradually on spring causing a deflection of 300 millimeters. So now energy stored in the spring. Energy stored is half of, is if a gradually applied load, half of F into delta. We know this. But there are two springs, that's why multiply it by 2. Okay. So here, no, this two gets cut. F delta will be there. F delta, delta is 300. We know 300 F. So if this is 300 F, and this is this, you equate this kinetic energy to the energy stored in the spring. So all the kinetic energy of the wagon will be stored in these springs. So from this, no, you can get F. You see here we have already considered 2. That means what, this force that we are getting. What? How are you getting this? This F into 300 is equated to 62 point easy 62.5 into 10 to the power 6 Newton millimeters. Okay. Then F you will get this value. So this is the force coming upon each spring. Okay. Then torque transmitted by the spring, that is T is equal to F into dm by 2. F we have just now calculated into dm by 2, so you will get the torque. Okay. Now T we have 5/16 tau d cube. From this you can get one diameter. Okay. And if for getting the number of turns, use the delta formula. From delta, from this you can find out uh, number of turns. You can use a C, because C is equal to dm upon d. Otherwise you can use capital D itself directly in this, no need of this. Okay. And you can find out n is 5.43, that is 6 you take. Then assuming square and ground ends, this will be n dash will be n plus 2, that is 8. Okay. Then the free length of the spring. Free length of the spring uh, is free length of the spring is LF is equal to n dash t plus delta maximum plus 0.15 delta. So you put this and find out the pitch also. Okay. But in this problem, we could have used for finding this, instead of using all this now directly, we could have found out the Wahl's correction factor, and you could have used that equation, tau equation. We are having two equations. That way also you can do, no problem, because in the question nothing, they didn't say neglect curvature effect, they didn't say. Okay. So you could have used that way also. Okay. So you can keep solving number of problems like this. So with this we stop solving the problems, and with this we have come to the end of this unit springs. Okay. Now this unit springs also we have covered. So totally out of our syllabus, out of 6 units we have covered 5 units, and next we will cover the 6th unit. So today we'll stop here. Thank you.